Hello, this is Professor Kuehn and welcome back to my lectures on electricity, magnetism, and light. In my previous lectures, we spent some time talking about the work of Michael Faraday, who was one of the most important scientists in the 19th century. His experimental work laid the groundwork for the modern electromagnetic theory of light. So now let's move on to the work of James Clerk Maxwell. He was a theorist that put together the electromagnetic theory of light in its theoretical form. We're on Chapter 30, Action at a Distance, in A Student's Guide Through the Great Physics Texts, Volume 3. So bear with me. What I plan to do is read through this and make comments as I go. So we're on page 379. James Clerk Maxwell was born in 1831 in Edinburgh, Scotland. As an adolescent, Maxwell's father enrolled him at the Edinburgh Academy, where he excelled in drawing, geometry, and English verse. Recognizing his son's aptitudes, his father began to bring young Maxwell to meetings of the Edinburgh Society of Arts and the Royal Society, and by the age of 15 he had contributed a mathematical paper to the proceedings of the Edinburgh Royal Society. Maxwell went on to attend the University of Edinburgh between 1847 and 1850, where he carried out original laboratory experiments on polarization of light and chemistry. He attended philosophy lectures by William Hamilton. He perused high-level scientific works such as Young's lectures. Remember, we've read some of Young's lectures. Fourier's theory of heat. Fourier came up, by the way, with what are now known as Fourier transforms. Fourier's theory of heat and Newton's optics. And again, you've read some of Newton's optics in this class. And Young also published 2 mathematical papers on the theory of rolling curves and on the equilibrium of elastic solids. He entered Peterhouse College in Cambridge, where he spent 1 term before migrating to Trinity College. He graduated in 1854 and attained a fellowship and lectureship at Trinity until 1856. He then served as a professor of natural philosophy at Marischal College in Aberdeen for 3 years before moving to a position as professor of physics and astronomy at King's College in London until 1865. During his time in London, Maxwell was occupied with formulating his electromagnetic theory of light. In 1871, Maxwell was elected an honorary fellow of Trinity and became professor of experimental physics at Cambridge. In Cambridge, he oversaw the erection and furnishing of the Cavendish Laboratory, which is still a famous scientific laboratory in England. Maxwell is best known for his work on the kinetic theory of gases and his electromagnetic theory of light. So first, on the former topic, the kinetic theory of gases, regarding this former topic, Maxwell argued that the macroscopic properties of a gas, like its pressure and its temperature, may be understood in terms of the velocity distribution of the particles comprising the gas. What that means is that we have these common sense notions of the temperature and pressure of air, for example, in a balloon. And he said all of those properties, pressure, temperature, volume, and so on, can be understood in terms of this atomic theory, that is, treating the gas as a collection of particles that are zipping around with a particular distribution of speeds. Regarding the latter topic, that is the electromagnetic theory of light, Maxwell drew together disparate lines of research from electricity, magnetism, and the wave theory of light to argue that, quote, light is an electromagnetic disturbance in the form of waves propagating through the electromagnetic field according to electromagnetic laws. So remember, in this class what we've done so far is we've treated electricity separately and magnetism separately and light separately. And now we are unifying them into an electromagnetic theory of light. And this is essentially the work of James Clerk Maxwell. Maxwell's electromagnetic theory of light, presented to the Royal Society in 1864 as, quote, a dynamical theory of electromagnetic field, was inspired by Faraday's conception of electric and magnetic forces as manifestations of strains arising within a subtle medium pervading space. Underlying Maxwell's theory is the idea that electrically charged bodies do not act upon one another immediately, that is, without any intervening medium. Rather, forces between bodies are mediated by the luminiferous ether. The conflict between natural philosophers who advocated action at a distance and those who advocated mediated action is a topic of the reading selection included in the present chapter. It was first published in the Proceedings of the Royal Institution of Great Britain in 1873. Whose arguments do you find most convincing? Okay, so what we're going to be doing is we're going to be looking at this article that Maxwell wrote, and you have to keep in mind, as I mentioned in this introduction, that there are really two competing schools of thought. One school of thought said that if one object over here acts on or exerts a force on another object over here, that action must be mediated by something going on in the medium or the space between them. So for example, Faraday will be an advocate of this. He says if there's a magnet here and it pushes on this magnet, things can't push on things where they are not. Things can't act across empty space without something happening in the space between them. So Faraday conceives of this magnetic field being generated by this magnet. That magnetic field fills the space and then acts on this magnet over here. So that would be a mediated action. The advocates of action at a distance will claim the opposite. They'll say this magnet right here pushes on this magnet right here without anything going on in the intermediate space between them. It's almost as if it's simply a property of this to push on this. You don't need to appeal to anything going on in the space between them. So this is the debate that you're going to be seeing that you will be seeing playing out in this article that we're reading. Notice what Maxwell is also doing here. Like a good debater, he begins by presenting his view, but he also is able to present the opponent's view in a very clear and concise way, which is something you always want to do in debating. You want to explain the opposing viewpoint with such clarity that your opponent wishes they said it that well, and then proceed to dismantle it. So you can decide how well you think Maxwell is able to do this. Okay, so let's go ahead and start into the reading. Maxwell on Action at a Distance from 1873. Maxwell says, I have no new discovery to bring before you this evening. So he must be doing a lecture in front of people. I have no new discovery to bring before you this evening. I must ask you to go over very old ground and to turn your attention to a question which has been raised again and again ever since men began to think. The question is that of the transmission of force. We see that two bodies at a distance from each other exert a mutual influence on each other's motion. Does this mutual action depend on the existence of some third thing, some medium of communication occupying the space between the bodies, or do the bodies act on each other immediately without the intervention of anything else? By the way, for those of you who are interested in theology, there are similar kinds of questions being asked about things like the sacraments between theologians around this time and before this. So some might argue that God can bring one to faith or bring one to salvation immediately, that is, without using any material substance. And those would be some of the Protestant denominations who would claim that God basically can bring someone to faith apart from any means. And then there are other theologians who will claim, and this is typical of Lutheran theologians, who will claim that God brings people to faith, but using the medium of word and sacrament. So there's sort of this medium that God uses in order to bring people to faith. So wherever you stand on those theological issues, I think, or whether you think about them at all, I think it's interesting to see some of these theological debates having analogies in scientific debates that are happening during this time period, and in fact throughout most of history. Anyhow, the mode in which Faraday was accustomed to look at phenomena of this kind differs from that adopted by many other inquirers. And my special aim will be to enable you to place yourselves at Faraday's point of view, and to point out the scientific value of that conception that lines of force, which in his hands, that is Faraday's hands, became the key to the science of electricity. So Maxwell here is saying that he is going to try to be an apologist, so to speak, for Faraday and his conception of lines of magnetic force, or lines of force more generally, that is, of mediated action. When we observe one body acting on another at a distance, before we assume that this action is direct and immediate, we generally inquire whether there is any connection between the two bodies. And if we find strings or rods or mechanism of any kind capable of accounting for the observed action or force between the bodies, we prefer to explain the action by means of these intermediate connections, rather than to admit the notion of direct action at a distance. So Maxwell is here saying that this is the common sense perspective that you and I employ on a day-to-day basis, is that if something pushes on something else, we right away look for some way that force is communicated between them, right? So I mean, think about a magician who appears to be lifting up a person off of a table. What do? Do you think, oh, well, that magician is immediately acting on that person? No, you think there must be some strings attaching them, right? So he's saying this is our common sense approach. He goes on to say, thus, when we ring a bell by means of a wire, the successive parts of the wire are first tightened and then moved till at last the bell is rung at a distance by a process in which all the intermediate particles of the wire have taken part, one after the other. We may ring a bell at a distance in other ways, as by forcing air into a long tube, at the other end of which is a cylinder with a piston, which is made to fly out and strike the bell. We may also use a wire, but instead of pulling it, we may connect it at one end with a voltaic battery, and at the other end with an electromagnet, and thus ring the bell by electricity. So, what is Maxwell doing here? He's reminding us of various ways that this force can be communicated from one thing to another. As an example, he's using ringing a bell. So when an usher at church rings a bell by pulling on the ropes hanging down the belfry, the rope is tightened and it acts on the bell way up in the bell tower, right? But you don't have to use a string. One could use an air piston. So push on air and that would ring the bell. Or one could, like in a modern doorbell, send an electrical signal down a wire that in turn would ring a bell. All of these are mediated actions. So here he says, are three different ways of ringing a bell. They all agree, however, in the circumstance that between the ringer and the bell, there is an unbroken line of communication, and that at every point of this line, some physical process goes on by which the action is transmitted from one end to the other. The process of transmission is not instantaneous, but gradual, so that there is an interval of time after the impulse has been given to one extremity of the line of communication, during which the impulse is on its way, but has not reached the other end. It is clear, therefore, that in many cases the action between bodies at a distance may be accounted for by a series of actions between each successive pair of a series of bodies which occupy the intermediate space. And it is asked by the advocates of mediated action whether in those cases in which we cannot perceive the intermediate agency, it is not more philosophical to admit the existence of a medium which we cannot at present perceive than to assert that a body can act at a place where it is not. So after having mentioned a few examples of mediated action, he recognizes that there's some cases where it is not clear how one thing acts on another thing. And he says, but isn't it more sensible, more philosophical to say, well, maybe we just don't know, we don't understand yet the medium through which that force is being communicated. And he's saying, asking rhetorically, isn't it more philosophical to kind of look for that mechanism by which that force is transmitted across only seemingly empty space? And now he goes on to give an example of how that process has worked out in the past. He says, to a person ignorant of the properties of air, the transmission of force by means of that invisible medium would appear as unaccountable as any other example of action at a distance. And yet in this case, we can explain the whole process and determine the rate at which the action is passed on from one portion to another of the medium. So he's saying even in some cases where you cannot see or immediately detect the medium, we know that it's there, and we found out later that it's there. So think about when you speak. And when you speak, sound comes from your mouth, and then your ear detects that sound across the room. Well, it's not clear to those who first started studying this that there is air that is being compressed and expanded in the region between my mouth and your ear. It might seem at first that this is action at a distance, and he's saying, but upon further study and reflection, it becomes clear that this is a mediated action. And then he goes on to say at the bottom of page 381, why then should we not admit that the familiar mode of communicating motion by pushing and pulling with our hands is a type of and exemplification of all action between bodies, even in cases in which we can observe nothing between the bodies which appear to take part in the action. So shouldn't we just take this as a paradigm, as the way we should always be thinking about the transmission of forces? So here he's really pushing this mediated action perspective. Now he goes on to give an example, once again, of something that seemed to be an immediate action at a distance, that turned out to be a mediated action. He says, here, for instance, is a kind of attraction with which Professor Guthrie has made us familiar. So he's presumably in this lecture now giving a demo or demonstration. I'll draw a picture to show what he's talking about here in a moment. He says, a disk is set in vibration and is then brought near a light suspended body, which immediately begins to move toward the disk, as if drawn toward it by an invisible cord. Okay, so think about it this way. Suppose that you have a disk like this, and you put it on a shaft, and you begin spinning it. You can either vibrate this back and forth or spin it at some high speed. And now suppose that we hang in front of it a tiny thread and a very light little pith ball or some other light object. And as you spin this disk, you notice that this ball begins to be attracted toward it. It looks clearly like it's being pulled toward it. In fact, it is being pulled toward it. Why is that? It's not like there is a cord attaching these, so what is causing it to be pulled? He goes on to say, Sir William Thomson, Lord Kelvin, by the way, of the Kelvin temperature scale, Sir William Thomson has pointed out that in a moving fluid, the pressure is least where the velocity is greatest. The velocity of the vibratory motion of the air is greatest nearest the disk. Hence, the pressure of the air on the suspended body is less on the side nearest the disk than on the opposite side. The body yields to the greater pressure and moves the disk forward, moves toward the disk. So he's talking about what's now called Bernoulli's principle, that when you have a fluid medium like air, that air, if it's moving at high velocities, has a lower pressure than the same air moving at low velocities. So if there is air in the region all around this disk and all around this ball, the air that is near the disk is going to be moving at high velocity. It's being dragged around by the disk. It has high velocity, whereas the air farther away from the disk is moving at low velocity. And by Bernoulli's principle, the high velocity air has low pressure, and the low velocity air has high pressure. And as a result, what happens is the high pressure air pushes that small light body toward the disk. He said the disk therefore does not act where it is not. It sets the air next to it in motion by pushing it. This motion is communicated to more and more distant portions of the air in turn, and thus the pressures on opposite sides of the suspended body are rendered unequal, and it moves toward the disk in consequence of the excess of pressure. The force is therefore a force of the old school, the case of vis a tergo, as he translates from Latin, a shove from behind. So this is another example, he says, where it seems as if this disk is acting immediately on this light object, but in reality, there is this medium surrounding it that's communicating a force to this ball and pushing it from behind toward this disk. Maybe I'll just give a couple of other examples of how this Bernoulli's principle works that you might be familiar with. I don't know if you've ever been driving your car on a freeway and you get a flat tire. This has happened to me. And you have to get out of your car and change the tire on the side of the freeway. And it's actually a very scary thing to happen, because sometimes what will happen is a semi, a very big tractor trailer, will come by you at very high speed, 60, 70 miles an hour. And when it does so, it feels for a moment like your vehicle and yourself are being kind of sucked toward the semi. You kind of get rocked over in that direction. And that's precisely the same kind of thing. This high velocity air suddenly has low pressure, and the high pressure air on the other side of you pushes you toward the semi. And maybe, I think I don't have a sheet of paper here. I do. Let me get a sheet of paper. I'm going to show you one more example. Okay, here's another example of the same thing. I have two sheets of computer paper right here. And if I hang them straight up and down like this, They are hanging vertically. Now I'm going to blow between them. Notice how they get attracted to one another. That is because the high velocity air has low pressure, and so the pieces of paper get attracted to one another. Okay. Now, in what he's done so far is he's tried to argue in favor of mediated action. Now what he's going to do is begin to take the perspective of those who argue for action at a distance and argue their perspective. So let's take a break there and come back to this shortly.